Disc is spinning. Okay, should be any moment now.
Uh-huh. Mm-hmm.
By golly, we are ready, ladies and gentlemen, once again, to kick around the cosmos for the 110th episode of the SBAU Astro Hour online, the weekly blog podcast for the South Coast of Central California's longtime telescope and astrophysics club, the Santa Barbara Astronomical Unit, based up at and supported by our Museum of Natural History. Just 93 million miles of facts and fun and frivolity from the sun, everybody. This program, number 110, is for Monday, March 27th through next Sunday, April 3rd, 2023. The week after that, on Friday night, the 7th of April, we'll have our next meeting. Watch us on YouTube live every Monday morning, 11 to noon, and use our website, ladies and gentlemen, sbau.org, to see past programs. I'm Ron Herron, your host. We're going to cover a lot of good stuff today. I hope I don't get lost, especially in that stuff about space-time emerging. My God, if you didn't know it, you're going to learn how fast we're moving and where and in how many different directions. My God, you won't believe we're booking, folks. It's like driving a Tesla. And we're going to catch up on Venus and Mars, and I think there's a divorce up there with Jupiter, and we'll check with one of our talkers here. The coming first quarter of Cynthia, that's our lovely moon. And we're going to consider the dreaded cosmic microwave background, green and orange speckles and what it all means. Consider the neutral hydrogen, there you go, and try to merge, oh my God, string theory with general relativity somehow, if we get to it this hour. Catch up with NASA's latest gyrocopter. This one's called the Dragonfly. It's destined for Titan, the moon of Saturn. Let's meet everybody. I'm Vice President. Here's our president to my left on the screen. In white, Jerry Wilson. Jerry, congratulations on 5 years, going on 6, isn't it?
Thank you, I think.
How long have you been married to Pat Forgy? Just out of curiosity. How long?
22 years.
Oh, you guys starting to get serious about each other.
We've been married 57 years.
Okay, well, I'll ask you that when I get to you, Bruce. To my right on my screen with the flag of Ukraine behind him is my good friend Chuck McPartland, our outreach coordinator, who's going to give us some dynamite reports here in a second. On the bottom is Bruce.
Actually, it's been 59 years.
Say again?
I said it's actually been 59 years. I just did the arithmetic.
How do you guys stand each other after 59 years? That's a lot of time to be living with the same person, Bruce, but she must be wonderful. Her name is Bonnie.
Right.
And you are a longtime active member of the club, SBAU, and as well, you run the Santa Barbara Theater Organ Society as their president. But I think you like sky stuff a lot better. In fact, we're going to post some of your pictures later. You're not going to believe the Messier. What is that called again, President Jerry? The Messier March? No, the
Messier Marathon.
Marathon. That's still going on. Here is Tom Whittemore, who's married to Maureen, former Westmont College science instructor, one of the greatest bakers of sourdough bread you'll ever want to see in your life. Got a couple of little items. Our beautiful museum is saluting condors in the next week or two. I believe it's 6:30 to 8 p.m. on the night of Monday, April 10th, 2 Mondays from now, downtown at Gargan's. They sent that out. Thought I'd give our benefactor, big, beautiful museum, a little shot on that. We did go to the Ritz Bacara Resort, and you posted our, I guess, April outreach, Chuck. How was the Bacara? Are we back permanently, you think?
I don't know. They just wanted to do that. They said as a trial run, to see how we operate. It's new people there because they get sold every couple of years.
That's true. Yeah. So we just call them Ritz Bacara. What did they call them before? Who owned Bacara?
It was Bacara at first, and then it was the Bacara Resort and Spa, and now it's the Ritz-Carlton Bacara.
Mm-hmm. And
it's been that through a couple of sales, actually.
All right. In the posted email exchange you had that we all got, for schools and education, we don't charge anything, do we?
That's correct.
But if it's something like a money-making, business,
then we ask for a donation to the club.
To the club through the museum. Got it. Some pictures being taken by anybody in particular through their cameras and their telescopes. Tom Whittemore, what? You want to give us a night sky view?
I just do binocular astronomy. I don't do photographs, so I don't do imaging.
You don't?
The weather
I
was
used to
not
do
been
well.
in our
I did it
favor.
scientifically at Westmont, you know, when I had students there. But no, I enjoy just looking at things. And you know, lately there's basically a parade of planets. A pair of planets, Mercury and Jupiter, are going to be kind of tough for the folks to see. I'm talking about the western sky. There's a whole parade of planets. But last night with binoculars, and my bird binoculars, my 8x42s, I was able to pull out Uranus fairly close to Venus. It was up and to the left of Venus last night, if you look to the west. But as the week goes on, Venus will keep climbing and climbing and climbing in the western sky. Uranus is basically not moving much at all out there. And what you'll see is a real nice launch point. So you can use Venus as a launch. Uranus itself is going to glow blue. It's not going to twinkle. So that's the thing. If you have a small telescope, it's real easy. Okay. Binoculars, a little tougher. But last night, the magnitude of Uranus, I think, was like 5.8. So it was pretty easy to pick off. But there's a lot of background stars you have to, you know, shuffle through, if you like.
Yeah. Is Uranus the gas giant that's turned on its side?
Yes.
Yeah.
It's a,
Okay, but the James Webb recently released a photo it took. I'm not sure if it's up here or not later, but it shows the rings around one of them. Was it Uranus?
That was Neptune.
we did that a while ago.
That's way out here. Yeah. All right, so we're starting with the night.
Oh, thanks, Jerry.
I just sent Jerry a couple of pictures of the lunar eclipse that I took on the 8th of October, 2014 at Westmont. And it was just happenstance that, and I didn't know it until I processed my pictures, that Uranus was in the blood moon picture.
Really?
You know, because of the moon is not bright when it's in a lunar eclipse. So
yeah, I remember that night, Bruce. We had hundreds of people out at Westmont. I'm sure Chuck remembers that too.
Yeah. This is what Tom was talking about a moment ago. Here down on the horizon, this is the sun. You can see the sun is still. It's not completely through dusk, but there's Jupiter, and between the J and the U on Jupiter is the icon for Mercury, which is down here. So they're real close together, like a couple of headlights just before they set. This is about 10 minutes before they set, or 10 or 15 minutes after the sun sets.
Tough grab, Jerry.
Yeah, I had to work on this with my planetarium software, and then Venus and Uranus as they're discussing here.
Right.
And the Pleiades up here with the name of all the individuals.
Yeah. And it was a few nights ago, I was just going to mention, it was really pretty to see the moon just after the equinox, because when you have the setting, when you have the moon in the western sky after the equinox, it looks like a little smile because the ecliptic is cranked almost vertically. You know, that's when you're going to get the smile looking moon in the springtime.
Yeah, this was taken. This shows Venus and the moon. I stole this from Facebook. It's not my picture. So this was late last week, about a 3-day-old moon in the western sky, low below Venus, or but just above Venus. It's now about almost a first quarter.
Yes.
So it's dramatically different at this time.
And these are real high first quarters. So in March, the first quarter moon is almost right over your head here.
It ruins the whole sky for photography. So it's an equal opportunity ruiner. Among pretty pictures this week.
Go ahead.
Among pretty pictures this week was this one I captured from NASA. It shows noctilucent clouds on Mars. So this is after sunset in the night sky, and the clouds are above the horizon and in sunlight, but the terrain down here is dark. So
when I first saw this, I thought we were looking down at the planet, and the curvature of the horizon was the edge of the planet. We were looking at the orbiter.
You're right. This is the edge of the planet.
Yeah.
But it's not what you meant.
It's just the horizon.
Well, we do have an orbiter up there. Maybe it can look down on that same cloud.
We have several orbiters up there. Yeah.
Okay.
And one of them is optimized for looking at the atmosphere.
Mm-hmm.
And that cloud is water vapor?
It's ice crystals.
Oh, really?
Does it rain on Mars?
No.
No.
Pressure is too low.
Hail wouldn't come down from ice crystal cloud. Okay.
I think it's more the case of dew precipitating out of the atmosphere. Because you do get coverage of things with ice. The ice,
they get
polar
frost.
caps can extend.
But with direct sunlight, it doesn't get that warm on Mars, does it?
It can get up to 70.
Can it really?
It's not often.
And Ron, do you know what the pressure is read on Mars?
No, what?
Mars bars.
Ah! Hey, now that reminds me, Mr. President, we missed our cartoons.
Oh yeah, gotta have
Gotta
those.
go back and get some levity. So this is like upcoming news here, or what we've been seeing is breaking stuff. And I'm glad that's not taken from Ingenuity, the helicopter. We're going to talk about another helicopter later called the Dragonfly, but let's go to the silly stuff that our beloved president forwards to us. See if I can match what I've written down as I look at them and laugh. Little levity. These are just setting the mood, and we'll get into the really serious stuff. Hopefully able to make you all understand. I'm going to be right with you on some of this stuff, wondering. Okay, here comes the first one, we hope. We also need to get a new Chrissy Cook. Oh, here we are. I have an old farmer outside looking, and what is this one? Captain, says one of the aliens inside the spaceship. Captain, we are now in position, have been sighted, and the Earthling has us in his viewfinder. And the other one says, excellent, activate the blurry photo effect force field. Don't worry about. That happen to you guys all the time?
Yeah.
Either that or let go of the marsh gas.
Yeah.
Yes, yeah.
That's
You know, all these cameras everybody has nowadays, and no one can get a clear picture of a UFO.
That's true.
You know, those saguaro cacti in the background remind me that somewhere this week I saw a decal or a sticker for Lompoc, and it showed rocks and saguaro cactus and said Lompoc. It was like, what?
Nope. I went to school in Tucson. I went to school in Tucson, Chuck. Swamp over there. In fact, the state flower is the blossom.
Well, here's for all the cat lovers and owners, and that's most of us. A couple of aliens have just exited their ship in the backyard. Yeah, I'm their leader, says the cat at the window. What do you want? That's got to be Chuck's. And incoming, it's an asteroid about to wipe out two guys who are coming down from something. They're in, what are they doing? They're convalescing. You're kidding. I was struck by lightning twice too. My God, that never happens. You're about to be obliterated.
Bad luck.
Yeah. Here, two cartoons are merging on the moon. And the astronaut from Apollo says, you know what? To the crawling guy on the sand of the moon, one of us is in the wrong movie. I'm sorry. I haven't identified who. This looks like a Far Side.
Yep,
Time
definitely.
Machines run out of gas. And it stalled him in the Plesiozoic era. Now this one you're going to need some explanation. The scuff marks the moon. Oh, I see. He leaves a trail and it makes a line, and you can even see it from your window. Is that what?
The line looks like the straight wall, but I didn't completely get that. But here you can see the line starting across the moon. Maybe he's trying to make something that is visible from Earth.
I think the joke here is mooning.
Oh, yes, you're right. Okay.
Oh, that's a butt? That's a crack? Okay.
It's the butt in the moon. Funny, I never would have guessed that.
That was my first thought, but I said they wouldn't put that in a.
Oh, no, no way, Jose. All right. Okay, the aliens are meeting an Indian chief, and one of them says to the other as they smoke away, we're not staying long, Chief. We're just not allowed to smoke on the ship. I like that.
And you can see a marijuana leaf back here.
Oh, my God. So we know what they're
Oh,
smoking.
yeah. Sharp eyes.
Yep. Okay, here's the lady standing at her husband's tombstone.
Backwards.
Yeah, and she says, I warned you about that time machine, Carl, and he was born in 1951, born and died 1924, about 26 years earlier. Okay, that happens.
27.
Make that larger, Mr. President. Uh-oh, we lost it.
Oh, no, we're done.
Oh, that was done already. Okay.
That was the last one.
Okay, how do we move through space? Anybody wondered about that? I have. There's a lot of different directions pulling on them. And the bottom line is we're going, what, about 600 miles an hour? Or is it a second?
The jump ahead per second, yeah.
Okay.
There's many,
if you take our latitude and our rotation, we're rotating it around 700 miles an hour to the east.
Okay, that's just rotation speed.
Yeah.
Yeah, that's just there's as we're finding out here, there are many types of motions, and the idea in relativity is that there is no absolute speed. You can only have a speed with respect to something. So, in a sense, to ask the question, can we get the Earth to move at, say, 20% the speed of light? If there's anything anywhere in the universe that's moving at 20% the speed of light, then we are moving at 20% the speed of light with respect to that object.
Wow.
So speeds are completely relative, and it has no inherent reference frame. Accelerations, you can tell. If you lock someone in a box, they can tell that they're moving, that they're being accelerated, but they can't tell whether they're traveling at any given speed or not. Now, your colloquial sense of common sense tells you that's not true, because when you're riding down the road at 30 miles an hour, you can definitely feel the speed of the road under it. But it's actually the pit holes, the potholes, and the irregularities in the road that you feel that are causing you momentary accelerations. It's not the speed you're feeling. Speed has no feel until you stop it suddenly.
Okay.
It's like they say, falling out of a building, it's not the fall that kills you, it's the sudden stop
at the end. Yeah.
Chuck, did you
bring
want to
up
say
an
something?
interesting point, with the speed of light, and this has always bothered me. They say, if you travel away at, some great percentage of the speed of light, say 9/10, and then you come back, you're going to be younger than your twin brother that was left on Earth. Well, if we're going with respect to the speed of light, or very close to it, with respect to something that we don't even know about, how do either one of us experience time dilation?
You think that time dilation should be symmetric?
The time dilation occurs because of the acceleration, not because of the speed.
Well, it depends. It occurs because the guy that traveled out there one way stopped, turned around, and came back. He's traveling in what's called his proper time. And back here on Earth, we're in a different kind of time called the frame time.
Yeah, Jerry, I can say it real simply.
Go ahead.
Moving clocks slow down.
Yes.
Okay.
When viewed from an outside reference frame.
Correct.
But to the guy that has the clock moving with him, that looks like it's moving at the same rate.
Yeah.
It's the same thing with traveling. If you got in a spaceship and you headed directly for a black hole, and an observatory on Earth was watching your progress toward that black hole, what the observatory on Earth would see is that as you get in the gravitational field, it strongly pulls you down and you speed up. But before you make it to the black hole's event horizon, you will slow down because of the time dilation. But on the spaceship, you would be looking back at the observatory, and things would be normal for you in the spaceship. The clock would appear to still be going the same rate with respect to your biological functions, but the universe outside would be speeding up drastically. Before you made it to the black hole surface, you would see the galaxy actually rotate and spin up because time is passing so fast outside compared to your reference frame inside, where it's slowed way down.
Mm-hmm. Yeah, I have a thought question for Ron again.
Uh-oh, I got to see. Here I go.
Sorry, it seemed like I'm picking on you, Ron, but you asked neat questions. And so I try to ask neat questions too.
Sure.
Let's suppose you were, and you can't do this, but let's suppose you were sitting on top of a photon. Okay.
Photon, okay.
On a photon, you're sitting on top of a photon. Okay. How much would your clock advance as you went about?
Well, it wouldn't.
Good. That's it.
That's why my little silly theory, and what I came up with that I was told, no, you're crazy, is time itself seems to be going through us at the speed of light. Is that possible? I mean, space-time is the same thing, aren't
You can't assign a speed to time. It's seconds per seconds.
Well, it goes, if you're going the speed of light, which is the speed limit in the galaxy, there's no time. So that means it's speeding along or whatever, present or stopped or whatever you want to call that. If we weren't moving fast through the galaxy, we'd probably age a little slower. If we were stuck, solidified, not moving, just in one place.
It depends who the observer is.
Right. It's all relative.
Anyway, if you want to know how fast we're moving through space, we have to look at a number of things because of that relationship of velocity being relative. You have to ask what it is that you're measuring the speed with respect to. So the first one is solely about its rotation, which is where we get our day from the Earth rotating on its own axis. Then it has motion relative to the sun, which gives us our years. We tend to measure it that way. Then there is, as this image implies, a relative to the Milky Way. And it takes about 220 million years for us to go around the galaxy once. So the last
Jerry,
time we were on this.
Jerry, you mentioned an image, but there's no image up, just to let you know.
Oh, you can't see this, Cher?
Right.
Sorry.
Yeah, because these are really, really good.
Can you see this now?
Yeah.
Okay. So relative to the Milky Way center, it takes about 220 million years to go around once. So when we were last in this position, there were Tyrannosauruses on our planet.
I think they were later, but yeah.
Yeah, they were later, Jerry.
Yes, there's an uncertainty in that. And you see, even though we calculate an orbit of the sun, to do that, at least in junior level mechanics class in physics, you assume that the center of the galaxy is a point source with all the mass of everything that's inside your orbit to hold you in that place. But you pass by so many objects that you can't rely, if you figure out an orbit right now, you can't rely on that orbit being unchanged for one rotation around the galaxy. So there's an uncertainty about that.
Right.
What if our sun was in a globular cluster or a star cluster? It would be corkscrewing around, it'd be running inside the cluster as well as around the galaxy, wouldn't it?
And we probably wouldn't be here.
Yeah.
That would add an extra motion. Then there's motion with respect to the local group of our galaxy.
Yeah.
And there's motion with respect to the large structure of the universe.
Yeah.
And we'll cover why that's a separate thing. Right. Or the leftover glow of the Big Bang itself, the cosmic microwave background.
Yeah. So if I might just add, I think of the sun as dragging the solar system around this galactic center. And I point out to people at star parties that there's a point in the sky where it seems to show where the sun is actually headed. And it's up near the keystone of Hercules. And it's known as the solar apex, solar apex. Yeah. It's just a neat thing to know. You point up at the keystone of Hercules, you say, wow, that's where we're headed. That's where we're being dragged.
In the galaxy.
In the galaxy.
That's correct. That's correct. Yeah. It's all relative. That's
now,
right.
This shows the sun and several of our planets. This is actually a video, but I snapped a picture of it. As it travels, the yellow line is the sun traveling around our galaxy. And this is the path that the planets make in orbiting the sun as the sun moves around the galaxy. So that...
and you can see that the corkscrews are tighter as you get closer to the sun.
Yeah.
Because those planets are going faster.
Well, do you suppose that angle that we are against the plane of the galaxy changes? Do we ever get flat with it, or just go over?
Well, the sun bobs up and down too. I mean, yeah, I don't want to.
Yeah,
I want Jerry to talk about his wonderful notes. They're just fabulous. But the sun does bob and down. I forget what the cycle is, but it goes up and down, in and out of the plane. So there's all kinds of crazy motions going on.
Well, it nutates too, doesn't it?
I don't think so.
I'm not sure.
I'm not sure about that. But there's an up and down bob that is periodic.
Bob, okay.
Yeah.
Yeah, it's because every time it gets seriously off the plane of the galaxy, the gravitational field of the galaxy will pull it back.
That's right. We get dragged back
until it's
like
the same as on the other side.
Like a pendulum going up and down.
And all the stellar systems have their own angles, right? They're not all the same as.
Yes, they're all random. When we look at the sky and look for exoplanets by looking at their light curves, when you look for an eclipse, those we only see that for systems that are tilted the same way we're tilted.
Really?
But there has been I don't know, I'm not sure if it panned out, but there was a study of planetary nebulae, and they often have jets, and so they have an orientation you can look at, a rotational axis. And a lot of them seem to be aligned with the magnetic field of the galaxy, as though that may have channeled how the gas formed into the star, the progenitor star, as far as its rotational axis got set. I don't know if anybody ever confirmed that, but there was one study that showed that these planetary nebulae seem to have aligned jets.
Actually, in thinking about my statement that their planetary plane is lined up with ours, that's not true. It's that their planetary plane is lined up with our, it intersects our Earth's orbit so that we can see its plane edge on. So it has to be oriented so that their planet can pass in front of their sun from our perspective.
You can see from Jerry's diagram here that the solar system plane is cranked about 60 degrees from the galactic plane. Yeah.
But basic question, gentlemen, does all star formation start with turning? Is it a similar phenomenon to our hurricanes on Earth?
Well, it doesn't start with turning, but turning is a result of the collapse because there's some net angular momentum.
Yeah. Our hurricanes are the way they are because they're confined to a two-dimensional sheet, a spherical two-dimensional sheet. They can't get in that third dimension into outer space to pick up another dimension. But you start with a galaxy, you start with a dust cloud that has completely random motion, and it doesn't have a really defined shape. But enough of it denser parts of it, individual particles will attract each other gravitationally, and they will either collide and stick or they will bounce off each other. And through these collisions, they will eventually come to an average motion, a shared motion. And this will cause this to become a giant spherical ball that's rotating. And under the attraction of gravity, the ball will eventually flatten out to a disk. It doesn't flatten into a point because the rotation, the angular momentum, causes one dimension of the sphere, the ball of gas, to not collapse. So that's why you end up with a disk.
No, they've never found a star that was just a collapsed gas and dust without turning at all. It just made a ball and therefore wouldn't have any planets orbiting.
I don't know.
No. There's going to be some net rotation.
Yeah.
So everything is turning in the damn universe, isn't it?
Yeah. It'll be unusual not to move.
It's a dynamic place.
Wow.
Yeah, you can't rule out that it absolutely could never happen, but it's not something that's very, very likely at all.
Yeah.
There's our neighborhood.
Here's our neighborhood. Here's the local galactic group, and star galaxies in that group are blue shifted. So
they're coming at us.
Yes, and the difference between there's two scales here. One is the local cluster, and the other is the Virgo supercluster. And the Virgo supercluster, let's see what the next picture is. Oh, yes. So on the scale of the Virgo supercluster is moving. There are things outside of us that it's moving toward. And these are views of other galaxies. These are the lines of motion that add vector sum to give us our motion. This is, we are moving away from this vacuums, this void, and we are heading toward this mass of galaxy or mass up here. On scales bigger than this, you notice the SGY. Okay, so
what is the lump called? Shapley.
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 Yeah.
Yeah.
Yeah, there's no E.
That's a mass concentration of some kind.
Yeah, it's a mass concentration of superclusters and galaxy clusters. And we are moving toward this. It's called the Great Attractor out in this deep region. This is also says it's the Great Attractor out here, but we by moving this way, we appear to be moving away from this void. And so that's the Great Pusher, if you want. So exactly what these are, they're just mass concentrations. But the important thing is that on scales bigger than this, then you come into what's called the cosmological principle, and that is that the universe is uniform in mass density, and it is also uniform or isotropic in mass density. So it's the same in every direction, and it's the same in every position. So you're averaging over every single point-like or condensation or collection of mass. And when you do that, that structure has, then we have a motion with respect to that structure on the cosmological scale that shows, this is the cosmic microwave background. It shows a Doppler shift. This is actually not a red shift and a blue shift. This is actually a heat diagram of a very small microkelvin scale. Shows that we are heading toward this area and we are moving away from this area with respect to the background area, the background microwaves. And that's the largest motion that we have.
Can you repeat the part? Are we going toward the red and away from the blue, or the other way?
Yes.
Okay, it doesn't make sense to me because I thought red meant it's.
Well, this is not a Doppler shift diagram. It represents our Doppler shift, but in terms of heat that we're going toward or coming away from.
Okay, so Ron, think of it as if you're blue shifted, that's higher energy, so it's warmer. And in this case, warmer things are being shown as red.
Yeah. An unfortunate choice of color by the person that generated this diagram.
Okay. So it's
rotational heating. Is that what you're basically looking at because we're moving toward the red?
Yes.
Okay. And that has something to do with the electromagnetic spectrum and
No.
not at all.
Yeah, it does in the sense that that's what we're seeing, but it's just showing our motion.
Okay. Well, what's the bottom line? Are we all going to collapse these clusters, these Virgo super?
What we've got is a lot of rotation around the galaxy, a lot of rotation around Earth. At any given moment, we are the vector sum of our velocities. A lot of these cancel out or cause fluctuations in other ones, but let's see if I can find the bottom line here. I know it's here. Overall, our total motion through space comes out to be about 368 kilometers per second toward the constellation of Leo.
About 200 miles an hour, right?
No. Much faster.
Per second.
Per second, yeah.
Per second. Geez, that's really moving. I don't feel it.
Yeah, and Ron, to give you an appreciation of the temperature scale there, on the right there with the red, that's 3354 micro Kelvin, 10 to my 6.
So 3,000ths of a Kelvin.
Yeah. It's very, very, very fine. These are probably since Kobe, right, Jerry?
Yeah, these are definitely since Kobe. Yeah.
Yeah. Okay.
But I got to tell you, gentlemen, I've seen that vast cosmic background thing, and it's got green and yellow. I think it's green. There's no blue up.
That's just how they chose to graph it and show you the different temperature differences.
Right.
And if you took that picture that you're thinking of that looks all modeled,
Yeah,
and you kind of averaged it, then this is what you would get. That there's a little more red on one side than there is on the other side. If they use their colors with red being slightly warmer and blue being slightly cooler.
am I looking at a little strip of green in the very middle of this picture?
Yeah.
There is a strip of green
Yeah.
in the middle there.
And it goes with the color code down there.
Yeah.
See?
Right.
It's all
We're
temperature.
just basically showing the colors of the rainbow going across.
Yeah.
Supposedly there are no green stars, and you gave a reason for that, I believe, or covered it recently, or maybe on this one.
A lot of that has to do with our perception of color, but yeah.
Yes.
Okay, gotcha. They're either blue or white.
Our sun's largest emission is in green, but our sunlight doesn't look green. It has a strong green component, but it looks to our eyes like white, yellowish white.
No kidding. Wow.
Yeah.
Okay. So 200
So
miles.
anyway, to look at the universe on the scale of this diagram, it would be neat to map out the hydrogen in the universe on that scale.
All right.
And the way you do that is to look at the 21 centimeter line of neutral hydrogen. And this emits in near the microwave background or near the microwave spectral area. And this shows an idealized hydrogen, a Bohr atom version of a hydrogen atom, the proton and the electron. And these arrows indicate the quantum number of spin. So this is an energy state of a hydrogen atom that is spin up. This represents the spin flip version of it. The spin quantum number is up, and here the spin quantum number is down.
On the electron.
Excuse me, yes, electron. Yes. So to get from here to here, this is an unstable state, and this is a stable state that's lower energy. And you see that when it flips, the whole atom has a lower energy state, and it emits a photon. The wavelength of that photon is 21 centimeters. And this is neutral hydrogen. It's the hydrogen you would like to see throughout the universe. We can measure it in our galaxy through radio telescopes. And this is a plot versus frequency. And this is the 21 centimeter band picked up by a radio telescope. And this is a map of the hydrogen, neutral hydrogen, unionized hydrogen in our galaxy. It sticks pretty much to the galactic plane, but there's things that sweep out too. It's also outside the galaxy, but we can't find that because our receivers are too small for it. So they're proposing a larger version of that telescope to be built on the moon. It's called the Lunar Crater Radio Telescope Project. It's got a 3 to 5 kilometer diameter crater with basically an Arecibo type radio receiver suspended over the crater, like we had in Puerto Rico before all the concrete gave out. So here it is. Ideally, it's looking away from the sun, which has a lot of excited hydrogen that's not neutral, past Earth, from Earth's noise. And this will be on the backside, and it's looking away into deep space.
In Arecibo, the concrete didn't give out. The steel rusted.
Well,
the steel cables.
Yeah,
Cables, right? They became dust.
Yeah, I thought it was the concrete with the reinforcing bars in it. That was
it was the suspension cables.
Okay.
Suspension cables, right?
They were braided cables, and apparently water could get inside there and persist.
Well, I think it was working when it got into the James Bond movie.
Yeah.
Residual damage, huh?
That's probably true. How are they going to dig this out?
They're not.
It's a crater.
They're going to
It's a
find
crater.
it.
Oh, well, craters aren't exactly designed to reflect radio waves from space. I would
suspend a mesh in it. It's the actual.
You'd have to build a mesh, Ron. You'd have to build a mesh there.
See the green there? Deployable wire mesh, the green stuff.
Oh, I see. Got it.
These
and
are
when
cables.
you think about the mesh, Ron, when you think about the mesh, you know, you're talking about 21 centimeters, which is about a foot, right? So the mesh has to be finer than that, right? That they basically plant there to get a good reflection.
A mesh will bounce back radio waves to the center point, just like a flat metallic
wavelength. If the wavelength is longer than the holes in the mesh mesh looks like a solid, shiny object to the light.
Good job, Jerry. That's it. Yeah.
You can see a horror movie with a giant spider coming out on that sucker. Wow. What if they find a monolith? Never mind.
Yeah. Just bring your earplugs.
Yeah, right. Would it be on the far side of the moon as depicted on the bottom of this picture?
Yeah.
So we got to go over there on the side we never see.
How do they get the information back? I guess they have to have an orbiter.
Oh, we'll probably have, I know there are plans to put infrastructure around both the moon and Mars, a GPS system, or what would it be called up there? An LPS system and an NPS system. And also communication satellites. So you would be able to contact the backside of either one of the moon, for example, just like you can contact the opposite side of the Earth here on Earth.
Wow. Earth noise. Our shadow makes noise.
Temperature makes noise.
No, this is low noise.
Well, I'm looking at the blue.
Oh yeah. Yeah, the Earth makes noise. As a matter of fact, and that's the dark side of the Earth. As a matter of fact, this is one of the things that we're looking for SETI, for search for intelligent life in the universe. We're looking for emissions that are not natural from the dark side of exoplanets, particularly in the IR with James Webb.
But the best time to look is at night, obviously, when the sun's on the other side, right?
Well, the best time, James Webb is always sort of out beyond the moon 4 times its distance and looking out away from the sun. And it's shielded from the sun.
Did any of you guys join SETI?
Yeah, yeah.
You did, Tom? So you
yeah. Well,
I did, but I don't keep it up.
Yeah.
Yeah. I've gone to meetings and stuff like that, and we lived in the Bay Area. And then for a while, when I was teaching at Ohlone College, I sort of let my my Mac, it's an old one, it was like a G3, an old one, to continuously, crank on data that was sent to it. So I just let it run,
Yeah, it was a system called SETI at home. And basically, if you
Mm-hmm.
had any idle time on your computer, it would go analyze radio data looking for signals. And they kind of stopped that now. I guess their budget really declined.
They don't do it anymore, Chuck. Yeah, I just did that for a couple of years when I was teaching at Ohlone College full time. Yeah.
Well, you also worry about hacking with all that stuff now.
So
and Chuck, do you remember the G3?
Oh yeah.
Okay. That dates me.
G3, what does that mean?
It was the processors.
It was a Macintosh computer. It's an Apple computer. This is a big chunk.
We're up to G5 now, right?
No, that's totally different, Ron.
No, that's entirely different. Yeah.
Well, there's millions of radio waves and there's millions of spots to spot them. So we're talking a long process, aren't we? Every spot in the sky and every frequency.
What they chose were sun-like stars within a certain distance, and then they looked at various radio frequencies.
Mm-hmm.
But you guys wouldn't have to have a radio telescope to get it. You came.
They would collect that data with large radio telescopes, and then packet it out to people to analyze.
I see. Gotcha.
But now James Webb is going to look in the infrared.
Oh, okay. Good deal.
Okay.
Lunar crater. All right. Was this taken, all these pictures, by our man there at the bottom of the screen, Mr. Murdoch?
No.
I found the Messier pictures like this on the web many years ago. And then I went through and amplified it, added the numbers, and put a bunch of my own photographs in there, like M42, which is over on the left, the third one down. And this is a very high resolution picture in the way I have it stored. It's about 65 megabytes. So you can zoom in on any one of them and actually see the, the Messier object.
Yeah, I think this main picture before you modified it came from SEDS, which is the Students for the Economic Development of Space or something like that. And they have this Messier catalog pictures.
So this is the controversial Messier object. I know someone speculated last week that it was a comet and he put it down as a stationary object, and then a century later someone else looked at it and it's just these two stars. So it moved. Maybe he goofed. Maybe his telescope blurred these. Who knows?
Yeah.
Are they two stars?
This is up here because the Messier Marathon, even though it was optimum last week, it's still possible to get this possibly, but most of them this week, if you are so disposed.
Well, now they're either galaxies or star clusters, right? There's these
are any faint fuzzy. He did not have a very good telescope, and these are all on different scales. Some of these are almost star-like, like the M1, M57, and some of these like M31, they're gigantic. This covers 8 full moons.
Yeah.
So he had a telescope. This is post Galileo. Yeah. Okay, he had
this one is the backdrop for my
your own. Is that 33? 33. Yeah, that's a beauty.
You know, just yesterday evening, M100, which is a face-on spiral, series was looked like it was superimposed on it.
Oh wow!
So people were going to image that. I don't know if anybody got a good picture. But yeah, there's M100 down near the bottom, and Ceres was going to photobomb it.
Yeah.
101 is similar too.
Yeah. Grand design spirals.
Yep. Yeah, I got my first view of 100 on a maiden voyage of my 18-inch that I built at Lassen, and it was just overwhelming. It was so bright. Eyeballs, no images, just eyeballs.
Yeah. This is a very big cluster. I think it's called the Pinwheel or something. And it's
Northern Pinwheel.
Yeah, and it's up near Ursa Major.
It's a cluster of stars. It's not
a galaxy, Ron. It's a spiral galaxy.
Yeah.
Okay, well, he just said cluster. Can galaxies be called clusters?
No.
No.
Only in error.
Okay. Got clustered down. But just like the stellar systems in our galaxy are at all kinds of different angles and planes. There's no standard for the universe as far as how these flat disks of galaxies stack up. Some of them are dead on, some of them are edge on.
Yes.
Yep. This is the sombrero.
This M104 is the Sombrero Galaxy. I was introduced to this by watching the closing credits of The Outer Limits.
Yeah. Well, not to break your heart, Jerry, but I saw it in a 61-inch in Tucson.
Oh, wow.
Yeah.
Okay.
Down the Outer Limits took over my horizontal, my vertical.
So this is a picture of the first quarter moon. A couple of features. The Mare Crisium, this circular floodplain of lava up there. And then Mars Serenitatis. And then that'll be just touching the terminator, and close to the limb is Mare Crisium. We discussed that. The bright rayed crater Stevenus is not obvious in this picture, but it is actually this crater right here. And at this particular time, now this is not a photograph of the moon. This is generated by a computer program. So it kind of blends in some of the outstanding features, but the reason this was picked out by Astronomy Magazine as a feature for this phase of the moon is because this crater has bright rays coming out from it. that are not shown on this mapping. So it's one of the easy and dramatic things to look at this phase.
But that's a quarter moon. Do you suppose there's a culture on Earth that would call that a half a moon?
Teenagers.
Yeah.
Or a
It's a
taco
quarter
moon.
way through its cycle.
Well, I know that there's 4 parts like this, but there's another side we don't see. But I wonder how many people know that or care about that.
Well, you have to clarify your set of people. You know, is it generally the scientifically illiterate? Sorry, folks, or the people that are interested in astronomy.
Yeah. And Ron, technically, we see about 59% of the surface of the moon because the way it bobs.
Yeah.
Bobs up and down relative to us, and also moves faster or slower going around us in that plane.
I know
it twists and it turns as it progresses.
Just like Chubby Checker.
Yeah.
the side that faces us has all the Maris, doesn't it? All the planes.
Not all, but most, yeah.
Yeah,
Most
all the
of
big
them.
ones.
Yeah.
Where's Albatignius in this one?
Where's what?
Oh, Albatignius. That's the one that you can see when the light's just right. You can only see the center peak for a day or two.
Moment. Well, this is Alphonsus, but I don't know where. I don't have any labels on that.
Does Mari mean sea, or is that MSR?
It means sea.
It does
sea.
mean sea. Okay.
Sea in
And
tranquility.
Maria.
Here.
Right. And the plural is Maria, Ron.
It's
In Latin. Yeah.
It's Italian.
Latin to me, Jerry.
It's what?
It's Latin to me.
Okay, it's Latin.
Yeah, 4 years of Latin. So it's
How did Latin transition to modern Italian? They certainly sound different.
Yeah, but when I
had
studied
2 years of Latin
Latin
in high
school,
school.
we pronounced Latin as if we were Romans.
I don't know that anyone knows how Latin was pronounced.
You get an idea when you listen to Romansh, you know, the language spoken in Switzerland.
Oh yeah.
You get a feeling for it. Mm-hmm.
And you could probably get hints from poetry that they would.
Yes, yeah. Mm-hmm.
I took Latin in high school, and in the second year, we were actually speaking to each other in Latin. I can't do that anymore.
We had to, where we got demerits. We were translating encyclicals and everything. You know, Catholic. It was a seminary I went to. So,
but when you read something, for example, the name of the city, Constantinople, or no, what was it?
Also Istanbul.
Sevastopol. Then you hear a native speaker, it's Sevastopol.
Yeah.
So if that guy was dead, you'd never know because you do it in your own language.
Yeah.
Yeah.
You emphasize the third syllable from the end of the word.
Yeah.
Well,
I think it's a syllable.
Yeah.
Right.
Did the world under Roman times live with VII and XII, Roman numerals before they?
Those are the numerals. Yeah.
See, that shows you why Rome would have never amounted to anything. Right. Science with Roman numerals.
Yeah. Boy, it's a mess.
Zero.
They had no zero.
They didn't have a zero.
Pardon? Roman numerals did not have a zero.
Yeah. The zero basically came from India through the Babylon.
Yeah.
Did they have sundials back then?
Oh, yeah.
They did.
A variety.
Sundials and moon dials.
Those are fun things to teach kids how to make, by the way, sundial.
No one understood the whys, but they were into empirical knowledge. They just noticed and recorded things.
Yeah. Yeah.
It's only when you got into science that you started putting together realistic mechanisms.
That's why we lost their way of doing concrete. You know, they made concrete that was super durable and self-healing, that the cracks would gradually fill in.
I heard that. Yeah.
They just learned it by mixing and matching and doing various things and seeing what worked. And then when that knowledge was lost, it's only now that we're recovering some of those secrets of what ingredients they had to put in to get those properties that they wanted.
Right. So now we have solid information on that.
And some of those ingredients were biological, like blood.
Mm-hmm.
So anyway, this is an interesting topic that is being covered in a vast article in Scientific American, and I clipped the next three visuals out of that Scientific American, talking about what is space-time. And at our level, you know, space-time, in one sense, you tend to regard it as nothing because it's like a vacuum. And a vacuum is when you remove everything from a given volume that you can remove, then what's left over is a vacuum. But a vacuum in this universe is something. It's not nothing. You can't move fast. It's a viscous medium. You can't move faster than the speed of light through it. And it's an expansive medium. It is that, but the word I'm looking for, it's an elastic medium.
Yeah.
As if you had a chunk of it and you squeezed it on the top, it would bulge out on the sides. And that's basically quadrupole gravitational radiation. And we get, because it supports gravity waves and we can now detect those, we know that it has to be an elastic medium. When something pushes on it, it responds and pushes back and overshoots and then relaxes. That's an elastic medium. But what is it? So we know it's the backdrop of the universe, but new research, theoretical research, tends to the idea that what we know as the universe are emergent properties of a deeper reality. That is, time and space are both high-level appearances of what's really going on. Now, for example, an emergent property is like the metal gold. You have gold, and if you cut it apart and cut it apart and cut it apart, eventually you come down to one atom of gold. And if you cut that apart, now it's not gold anymore. It has no gold properties. So gold on that scale, when it becomes an atom, it's an emergent property of the universe. It has properties that emerge from the way it's composed. So the idea is that space and time are both emergent properties that we tend to view the universe as. And there are two theories, string theory and loop quantum gravity, that people that work in this area, and it's purely theory, there is no experiment to this, that they have views of how these properties of space and time emerge. Space-time emerges from a more fundamental reality because of an idea called the anti-de Sitter universe. That's an early solution to one of Einstein's general relativity theory. And it's basically, it's a two-dimensional surface of a three-dimensional sphere. And the anti-de Sitter universe, as its interior connections between particles, it's basically made up of strings. Of course, it's string theory. Through a quantum process, the fundamental property of the universe, in this case, is called entanglement on the surface. It gives rise to regions of space inside that are located near one another. The stronger the entanglement, the closer the space regions are. So it's, you need to read the article. It goes into much more detail than I can do that.
Pretty hairy stuff, Jerry.
Yeah, with only 2 minutes left, it's going to be hard to cover this.
Yeah. The other one is loop quantum gravity. This assumes that space, the other one, the de Sitter universe, because it was a solution to Einstein's general relativity equation, the idea was that space-time is a continuum. It's smooth. There's no particles to it. But loop quantum gravity starts from a non-continuous space-time. That is, there are blocks or chunks of atoms of space-time. And it creates a spin foam with a one-dimensional or string connection. There are two-dimensional connections and one-dimensional connections between these atoms. So these blocks are very small, so small it's just incredible to think about the number even. But what we experience as continuous space-time through one-dimensional strings and two-dimensional sheets that connect the blocks. These links are what physicists call a spin foam. Oh. Now, these are all theoretical concepts. They come out mathematical. Yeah.
So Jerry, are these like in the Planck length? You know, really, really teeny weeny?
Yes.
Yeah, okay.
These are as far below our smallest length that we know, the Planck length, because the rules of our universe involve, you know, the fine structure constant and the Planck length and stuff like that. And this is below that.
Wow.
Because all those properties of our universe would be emergent from some other type of reality.
Right.
It's really mind-blending.
And Ron, the Planck length is 10 to the minus 33 centimeters.
Yeah.
And this is even tinier.
Yeah. So I recommend that you get a Scientific American and read the article. They elaborate much more on this stuff.
All right. Sounds good.
I just mentioned this stuff, but it's beyond my pay grade. Go ahead.
Can we bring this up again, maybe? Because I represent the crowd that doesn't have PhDs, that gets lost as laymen, if you will, and just have this fascinating appeal.
Well, Ron, to make you feel better, I've got a PhD and Jerry lost me.
Well, if it's any consolation, I lost me too. So,
well, then we definitely better talk about it in the future, if you don't mind, and try to make it understandable.
Yeah, great job. Notes again, Jerry.
Can I just quickly mention that Chrissy Cook is leaving, or I guess she's leaving, right? She's not going to be, and we need to replace her. And there's a letter posted from Chuck McPartland's outreach department from Luke Swetland. The general manager.
By the way, I just wanted to mention to Chuck that I am putting together the newsletter, and I have all the info that you sent me.
Okay, great.
All those little things, I'll put them in there, of course.
Okay.
Do you have the picture, Tom, of the guy that's going to talk from the University of Toronto to us?
You sent it to me. I have it. Okay.
Then we'll do this.
So anyway, the bottom line is the museum is looking for a full-time replacement for Chrissy Cook.
Yeah.
And they want someone that's an ardent, what does they call them, a fanatic on astronomy or something like that.
That's about astronomy is how it works.
And in other news, they were supposed to put in the new projectors in the planetarium yesterday, and it's been delayed till at least July and maybe July of next year. So we'll see.
Oh, brother!
And she's a school teacher. She's a teacher. Oh. Apparently,
she's a teacher. She's a music teacher.
Will Chrissy Cook be with us on our meetings, you suppose? Is she still in the club?
She'll still be in the club and in town.
Oh, sure. Yeah.
Okay. Well, then we'll see her maybe on the night of the 7th.
Yeah.
2 Fridays away.
Okay.
And
good night, everybody.
All right. We'll see you next Monday morning.
Bye.
For the